Welcome back, focused learners. I am your host, your chief strategist for today, and we are diving headfirst into an absolute masterclass on conquering your Cambridge physics examinations. Look, whether you're sitting syllabus 0625, 0651, 0652, 5054, or even if you're looking ahead to the 9702 A-levels, the principles we are decoding today, they are literally your stars to navigate by. I want you to imagine the tension of the exam room right now. You know that feeling, right? The clock is relentlessly ticking down, the invigilator is pacing, and you turn the page to find a massive, complex circuit diagram. We actually have a real Cambridge physics past paper question right here, focusing on the potential divider principle. And honestly, I see two typical approaches to this every single year. First, we've got Alex. Now, Alex completely overloads the page with raw physics facts, just dumping every single equation they've ever memorized onto the lines, but offering zero actual analysis of the circuit itself. And then there's Sam. Sam rushes. Sam is looking at that clock, completely ignores the command word requirements entirely, and just throws down a final answer, hoping for the best. And guess what? Typically, this results in brutal red pen marks from the examiner. Bam, 0 marks. But today, we are going to fix that. We are going to chart your course far away from those red marks and straight toward those top grades by decoding the actual secrets hidden inside the principal examiner reports. By the end of this explainer, we are going to transform those flawed, panicked approaches into undeniable, top-tier answers.
Okay, so let's quickly outline our exact flight path for today. We're covering 4 main areas. First, the core principles of potential dividers. Second, the procedural framework. Third, the method mark strategy. And finally, the top 3 examiner warnings straight from Cambridge. Let's jump right in. Starting with Section 1, the core principles. Top-performing students always exhibit a deeply connected conceptual understanding of these core principles before they even attempt to apply them.
Okay, so you can't just memorize formulas. You have to truly understand the why. Cambridge specifically wants to see knowledge, application, and analysis. To deliver this, top students use something we call the PEEL framework, point, evidence, explanation, link. Keep that in your back pocket. Now, the absolute core physics definition here is crucial. The potential difference, or PD, across a conductor increases as resistance increases for a constant current. This entire concept is guided by the fundamental equation R1 over R2 equals V1 over V2. This equation? It's the beating heart of the potential divider circuit. Think about a simple series circuit for a second. The current is constant throughout the entire loop, right? Therefore, according to Ohm's law, good old V equals IR, the voltage drop across any single component is directly proportional to its resistance. Think of the total voltage like a pie. If you have a variable potential divider and you increase the resistance of one component, it basically gets hungrier. It takes a larger slice of that total supply voltage pie. This conceptual framework prioritizes analytical depth over just superficial breadth. Remember Alex, our student from earlier? Alex would just write V equals IR on the page and pray for a mark. Sam would just scribble voltage goes up. Neither of them is getting full marks for that. To get those top marks, you must explicitly state that because the current is constant, an increase in resistance leads to an increased share of the potential difference. That's the PEEL framework in action. You make your point, you back it up with the physics explanation.
Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, I want to challenge you right here, right now, with a memory hack. You absolutely need to lock in how PD, resistance, and constant current interact in a variable potential divider. So create your own acronym, maybe something like PRCC, potential, resistance, constant current. Or honestly, maybe visualize a seesaw. Picture resistance and voltage sitting on the exact same side of the seesaw, so they rise and fall together, while current acts as the steady, unmoving fulcrum in the middle. When you were sitting in that exam hall, staring down a complex circuit diagram with a variable resistor, what mental trigger are you going to use to remind yourself that the ratio of the resistances strictly dictates the ratio of the voltages? This kind of active learning, actively building this memory hack in your brain right now, is exactly what separates the average candidate from the exceptional one.
Let's transition to Section 2, the procedural framework. Because knowing the theory is one thing, applying it is another. Knowing the physics is really only Act 1 of your exam. Act 2 is actually executing it under intense pressure. This is where we transition into the technical methodology required by the Cambridge Assessment Framework. We are moving from theory to what I call the physics success blueprint. Let's look at how a systematic approach ensures that every single time you see a potential divider question, you process it with total, absolute precision. Here is the 5-step standardized processing sequence to confidently tackle literally any examination question they throw at you. Step 1. Deconstruct the question and extract data.
Literally take your pen and highlight the command word. Are they asking you to calculate, explain, or determine? They all mean different things. Then extract the resistance values and the supply voltage and write them clearly on the side. Step 2. Select the analytical framework. For potential dividers, boom, it's our ratio R1 over R2 equals V1 over V2. Step 3. Execute with clear notation. This means showing you're working line by line, no scribbling in the margins. Step 4. Verify your results. This is a massive one. Does the total of your calculated V1 and V2 actually equal the supply voltage? If your battery is 12 volts and your components add up to 15 volts, well, you've just invented free energy, and you've messed up the math. Go back. Finally, step 5. Present with correct terminology. Don't write vague things like the electricity goes up. Say the potential difference increases. Now, imagine we rewrite Alex and Sam's answers live right now. If Alex applies this framework, instead of dumping facts, Alex extracts the specific resistance values. Those red examiner marks turn into green check marks. If Sam slows down, spots the command word explain, and uses the Peel framework to structure the answer, their mark potential dramatically skyrockets to 100%. The systematic processing is your ultimate weapon in the exam hall. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's shift into section 3, the method mark strategy.
This is perhaps the single most critical exam strategy you are going to learn today. Problem solving in Cambridge physics uses a very strict deconstruct, solve, evaluate workflow. The examiner isn't just looking for a magic number at the bottom of the page. Let me repeat that. They are assessing your cognitive process. They are tracking your analytical depth, step by step. Method marks are the safety net that top-scoring candidates exploit to maximize their grades even when they make a silly calculator error. The crucial point is captured beautifully in a recent examiner alert. Quote, "Students lose marks by not showing working. Even if your final answer is wrong, method marks can save you." End quote. Okay, let's launch into an interactive workshop right now. Challenge 1, data scan. Imagine a complex physics data table on the screen right now, showing varying resistances of an LDR at different light intensities within a potential divider circuit. You've got 60 seconds on the clock. What is the core trend? Scan it. The trend is, as light intensity increases, the resistance of the LDR decreases, therefore its share of the potential difference decreases. Simple, right? Now, if you just calculate that in your head and write down a final, accidentally wrong voltage at the bottom, you get 0, nothing. But if you clearly document step 2 of our framework, writing down the R1 over R2 equals V1 over V2 formula, and substitute the data from the table, you instantly secure method marks. The examiner awards marks for the process. You are literally buying insurance for your grades through clear, structured marking. Moving to our final section, top 3 examiner warnings. We're going straight to the principal examiner reports for this one. We are highlighting exactly where students traditionally hemorrhage marks year after year. Let's do challenge 2, find the flaw. I'm going to read a sample paragraph from a student. Listen closely and try to identify the sentence that is losing marks. Here we go. The variable resistor is turned up. This means the voltage changes, so the bulb gets brighter. Did you catch the flaws? Let's break it down. First, it lacks specific terminology. Turned up isn't a physics term. Is the resistance increasing or decreasing? Second, it completely fails to mention constant current. Third, it doesn't establish the ratio. This kind of descriptive, vague answer gets heavily penalized, which directly leads us into the 3 most common traps candidates fall into. Let's detail these. Warning number 1, using the wrong approach for the wrong context. I see this all the time. Students see a circuit and instantly apply parallel circuit rules to a series potential divider. Remember, a potential divider is fundamentally a series construct. The current is constant. Warning number 2, forgetting to check format and presentation. Leaving off units, like omitting the V for volts or the omega symbol for ohms, is a completely unforced error that examiners absolutely hate. It's throwing marks out the window. Warning number 3, providing answers not specific to the context given. If the question is about a thermistor in a fire alarm circuit, your answer must explicitly link the change in potential difference to the alarm actually triggering. Data interpretation is absolutely critical here. You must extract relationships from the provided tables and apply them to the specific real-world context on the page. Now for challenge 3, speed writing. Imagine you have 30 seconds on the clock. Try mentally constructing one perfect Peel paragraph explaining exactly how a thermistor's potential difference drops when the temperature rises, causing the secondary component's potential difference to rise. Point, evidence, explanation, link. If you can do that quickly, you've mastered this topic. This divide we've been talking about is perfectly highlighted by the difference between standard candidates and top-scoring candidates. Standard candidates, like our friend Alex from the beginning, focus heavily on superficial breadth. They memorize textbook definitions and regurgitate them onto the page, just hoping something sticks to the wall. But top scorers, they do something different. They demonstrate evaluative thinking. They consistently use the Peel framework we've practiced. They question assumptions, and they justify every single decision with hard evidence from the provided data. So, what is the final system here? It comes down to 3 rules that guarantee top marks. First, command word decoding. Are you explaining, calculating, or describing? Know the difference. Second, Peel framework application. Always use point, evidence, explanation, link for those written answers. And third, the time management matrix. You have to allocate your time based on the method marks available. If it's a 4-mark question, you need 4 distinct, valid points or steps of working. Don't write an essay for a 2-mark question, and don't write a single sentence for a 5-mark question. So, I leave you with this final thought. When facing your next potential divider circuit, will you just rush to the final answer like Sam? Or will you secure your grade by meticulously documenting the method mark strategy? Will you systematically deconstruct the ratio of resistance to potential difference? Will you fight to earn every single mark you deserve? Look, the physics hasn't changed. The only thing that changes today is your strategy. Master the potential divider, master the command words, and you will completely master the exam. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. Keep analyzing, keep evaluating, and I will see you in the next explainer.